Hi, my name is Joe Tavares. In this video, we discuss the design of the electromagnetic thruster. Electromagnetic thruster, EMT. For the thruster, we apply a magnetic field and we apply a current and we get a force, mechanical energy. The thruster provides lifting force against gravity. It converts electrical energy directly into mechanical energy. The meaning of the logo will be explained at the end. The current is circular and the B field is radial, or the current is radial and the B field is circular. In both cases, the force is straight. Okay, there's a paper here called Resolving Paradoxes of Homopolar Machine, and there's some experiments done for the motor effect, and the conclusions are the magnet is being held and the disc can rotate. The disc rotates. The disc is fixed on the magnet and can rotate. The disc rotates together with the magnet. The disc is being held, the magnet can rotate. The magnet does not rotate. The only explanation for the above three observations is the force is between the disc and the vacuum. The force on the conductor is between the conductor and the vacuum, like the propeller of a boat and the ocean. Okay, some legend. The direction is out of the page. Looks like a target. Think of a tip of an arrow. Red is for H field, black is for the B field. The direction is into the page with a cross. Think of the tail of an arrow. Red is for H field, black is for B field. The arrows, the direction is parallel to the page. It can represent a current carrying conductor or a B field. Red usually represents an H field. A square rectangle represents a magnetic core. The force equals the length times the B field times the current. To determine the force and direction between multiple magnetic fields, B fields, and currents I like to think in terms of interacting fields. The force direction is from a high concentration field to a lower concentration field. We have B as the field and we have I and want to represent the current as a field. The field that represents I is the H field, since H times L equals I. For B fields flowing into the page or out of the page, I use a black arrow. Both are out of the page or into the page. And for H fields, I use a red arrow to represent the H field produced by the I. For fields parallel to the page, I may use either black or red arrows, like black up or red up, or black down, red down. If the B field and H fields are in the same direction, that represents a high concentration field. If the B field and H field are in the opposite direction, that represents a low concentration field. The force direction is from the high concentration field to the low concentration field. Examples. Here we have H field coming out of the page and an H field going into the page. No force. Same concentration on either side. This example is the same as for a field around a current carrying conductor. Here the example, you have an H field going into the page as well as a B field going into the page, and you have a H field coming out of the page here, and you have a B field going into the page, or you have H field coming out of the page, a B field coming out of the page, and a B field also coming out of the page on the other side, and an H field going to the page. In this case, the force is from left to right, higher concentration on the left and lower field concentration right. It doesn't care about the direction, all it cares about is the concentration, both are in the same direction. Okay, so here are some examples. Current flowing in a conductor. This is a black arrow, which is a current flowing in a conductor, produces a field right around the conductor and produces no force. This case is no force. A current flowing in a conductor, black arrow, and an external B field present, black arrow into the page here, or out of the page, which is this case. The external B field must be in the same direction on both sides of the conductor and orthogonal to the current direction. So in this case, you have a force from the higher concentration to the lower concentration. Force from the higher concentration to lower concentration. Current flowing in a conductor, black arrow, and an external B field present, black arrow into the page or out of the page in opposite direction on either side. So in this case, the B field is in one direction out of the page here into the page there. In this case, there's no force because there's equal concentration on both sides. The external B field must be in the same direction on both sides of the conductor and orthogonal to the current direction to produce a force. Okay, in the last case, current flowing in a conductor, black middle arrow, and an external B field present parallel to the current direction, black arrow up or down, does not produce a force. The external B field must be in the same direction on both sides of the conductor and orthogonal to the current direction. So in this case, the B field is parallel to the current direction. So there's no force. So force equals I, current times the B field times the length. The length is the length of the current carrying conductor. Apply the left-hand rule to determine the direction of force, where F is the force in newtons, B is the external magnetic field in Tesla, T, L is the length of the conductor carrying the current in meters, and I is the current in amperes, A. Note the formula force equals IBL doesn't indicate anything about the source of the B field. It doesn't care. It could be from a parallel conductor, I2. So in this case, there's a parallel conductor here, and it produces this black B field, or from our orthogonal conductor I3, or from a permanent magnet. In this case, the current is 90 degrees to the I3 is 90 degrees to I1. It still produces a force. It still produces a B field, the same one on both sides. It still will cause a force. But I1 will not cause a force on I3. And or you can use a permanent magnet. There's a B field from the magnet, and it's both in the same direction here. Here the current is shown coming out of the page, and this is the H field produced by the current carrying conductor. Here both are in the same direction, which shows a higher concentration. And on this side, it's an opposite direction, which shows a lower concentration. So the force is from the high concentration to the lower concentration. A source is a high magnetic field concentration, like B plus H1, since they are in the same direction they are. A sink is a low magnetic field concentration, B minus H1, since they are in opposite direction. They subtract or cancel. Here's the B field produced in the air by a current carrying conductor or wire. Use the right hand grip rule to find direction. The vacuum permeability is 4 pi times 10 to the minus 7 Tesla meters per amps. Based on Ampere's law, HL equals I and B equals U naught H. L is the circumference at R. So this is the formula for the B at a given distance from the wire. H is the magnetic field strength, B is the flux density field, B equals mu H. For a core, use the BH curve established to establish the relationship. Force between the conductor and the vacuum. The force is between the conductor and the vacuum. It doesn't care about the source that is producing the B field in the formula of force equals IBL. Here's an example: two current carrying conductors in the same direction. The force on each wire is not between the two wires, it is between each wire and the vacuum. It just turns out to be equivalent as if the force is between the two wires. So there's the formula for the force on one wire. If we hold one wire above wire 2, the lifting force on wire 2 is only the force on wire 2, not the sum of the two forces, not the sum of the force acting on I1 and the force acting on I2. It's only the force of I2 is the lifting force, which also indicates that the force is between the conductor and the vacuum. So representation of two current carrying conductors, two parallel wires carrying the same direction, I1 and I2 in the same direction, produces H1, and I2 produces H2. I2 will produce H2 on this side. Inside they both cancel, so you have a higher strength, higher concentration on the left side here. You have a higher concentration on the right side here, and the force is to move the two conductors together. Now for parallel wires current in opposite direction, we have a higher concentration on the inside and lower concentration on the outside, so the force is to move the wires apart. It's away from each other. So what really is H? Electric current I produces around itself a magnetic field strength H, whose amplitude is independent of the type of a continuous isotropic medium, regardless of if it is non-magnetic, magnetic, nonlinear, etc. This is from a book by David C. Giles, Introduction to Magnetism and Magnetic Materials, 2nd edition. Electric current I generates magnetic field in the same form of a magnetic field strength H, regardless of the type of surrounding medium. So here's a current. So the representation is H on this side is out of the page, and this side is into the page. So what we can determine is H. H only relates to the current and not to any material, including the vacuum. Okay, here's some examples. So if you take a current carrying conductor on an external B field, you experience a force from right to left. But you can split this into two parts. You can first just show the B field on one side, and the force here is from neutral to the sink, which is half strength. And you can also show here that the B field on the right is from source to neutral and then a half, and the two is equivalent to 1. Here's the case for two current carrying conductors in opposite direction. It produces H field, the sum of the two, H1, H2, and if they're close enough, the H field here is 0, because it makes sense, because if you have a particle here looking this way, you have a current going in, a current going in the opposite direction, so the net current is 0, so it should produce no H field outside. So if we add a core between the wires, but this time instead of having both B field going, we have a B field coming out of it. So it turns out that there'll be a force this way, a force that way, but they will have 2 times the force this way. So it will be equivalent to as if it was a current carrying conductor, 2 times the current with an external field, so it will be a force times 2. Now we want to understand what are the forces on magnetically shielded conductors. And there's a paper in the Journal of American Institute of Engineers in January 1929 by J.H. Moorcroft and Alva Turner. The abstract reads: The result of some simple experiments are given to show how the magnetic force acting upon a current carrying conductor in a magnetic field is affected as the conductor is shielded by surrounding it by a permeable shield. It is shown that the force on the conductor practically disappears if it's put inside of an iron pipe, but that the pipe experiences a force. The sum of the force in the pipe and that in the conductor mean the same as that in the unshielded conductor. On a shielded conductor, the force does not exist on the conductor since it is shielded and no external B field is present around the conductor. The force is transferred to the shield with the same amount of force as if it was on the unshielded conductor. The experiment confirms that you can transfer the force from a current carrying conductor to a core. If the force on the conductor itself inside the pipe is now added to the force on the pipe, the sum gives the total force just the same as given by the conductor itself unshielded. The shielding therefore simply transfers the force from the conductor itself to the shielding material. How the force gets transferred from the conductor to a shielding core. Here I show a case where you have a current carrying conductor coming out of the page, but I put two shields. Just to illustrate. H is the magnetic field strength produced by the current I in red. So there's H1 here, H2 here. The current direction is out of the page. H1 is the magnetic field strength at core 1. L1 is the mean path length at core 1. H2 is the magnetic field strength at core 2. L2 is the mean path length at core 2. B1 is the flux density created in core 1, B2 is the flux density created in core 2. B equals mu H obtained from the BH curve for the core material, Ampere's law. HL equals I, L is the length of the closed path around the conductor carrying the current. H1L1 equals I, H2L2 equals I, H1L1 equals H2L2. It's not related to the flux density B in the core produced by the current, only with H. Note that the B field created by the current of the conductor T, the B1 or B2 fields are in opposite direction on the sides of the current carrying conductor, therefore cannot. So even if the current creates a B field, the B field is downwards here, the B field is upwards here, so there will be no force. So the current carrying conductor cannot create a force by amplifying the B field in a core. Bx, which is the external B field, the B field external is in the same direction on either side of the conductor. In the above example, it will produce a force on core 2 only, since the conductor and the core 1 is shielded by core 2. There is no Bx present inside core 2. B1 and B2 must be in the same direction on either side of the current conductor to be treated as an external field or to contribute to an external field. The external B field must be in the same direction on either side of the conductor for force to be created. So we'll look, there's an electromagnetic coil, the south pole here, electromagnetic coil on the north pole here. So we have a current carrying conductor coming out of the page. It produces H1 coming downwards, and the B1 produced by the current carrying conductor, and the B1 upwards here produced by an external B field on both in the same direction. If the force on the conductor itself inside the pipe is now added to the force of the pipe, the sum gives a total force just the same as that given by the conductor itself unshielded. The shielding therefore simply transfers the force from the conductor itself to the shielding paper. This is the paragraph from the paper. You would expect that by adding a core inside the air gap, the B field will increase, and that is true. But the reason the force on the core is the same as the force on the conductor is because the force is plotted against the B field. Therefore, the force at the given same value for B, whether with the case of air only unshielded or with the case of the core shield, will give the same force. It does not prevent the amplification of the B by adding a core. We want to amplify the B field by adding a core and eliminating the air gap. This will also greatly reduce the B field coil size, e.g. for B at 1 T for steel, H is 0.3 ampere turns per millimeter versus 800 ampere turns per millimeter for air. So here's the two graphs taken from the paper. It's plotted. So for the same air gap density B value, the force is the same value. This is not to say that by increasing the B value in a core, it will not produce an increase in the force. Example, from the graph above, with an air gap density B of 450 Gauss, the force is 30 grams in both cases. If we increase this B field to 4,500 Gauss 10 times by inserting a core, the force is transferred to the core, but the force will be increased to 300 grams 10 times. So what we want to do is we want to eliminate the air gap for the electromagnetic coil so that it will be easy. We only need small current to create the B field. We want to amplify the B field to around 1 Tesla by adding a core and eliminating the air gap. This will greatly reduce the B field coil size, e.g. steel 1008 with B at 1 Tesla requiring only 0.3 ampere turns per millimeter. But there is a problem with the B1 field, the red, produced in the core by the current, I1. Although this B field are in opposite direction on the sides of the core and cannot create a force, but to have a force large enough to lift a mass against gravity, it requires that I1 is very large, since the formula for force is F equals IBL. But I1 will saturate the core and no lifting force will occur. This will be explained in the next two slides for explanation. If we increase B as far as we can to 1 Tesla by adding a core, and this magnetic path contains no air gaps, now we want to have a large air gaps for the magnetic path produced by the current I1 to have little effect on the B field in the core. So here's an example why saturation caused by the current carrying conductor creates a problem. Say the core saturates at 1.5 Tesla. B black is the external field. B1 red is the field induced in the core. On the left and right side, B field is at 1 Tesla. B1 has no effect since it's in the opposite direction on both sides. Or another way of calculating is to break the force into sections. So we'll break the force for the left side and right side. B equals IL 1/2 B right plus B1 plus 1/2 B left minus B1 equals IL 1/2 1 Tesla plus 1/2 1 Tesla equals, that's if there's no current in I1. So case 1, we'll make B equals 0.5 Tesla and B1 0.1 Tesla. With B1 equals at 0.1 Tesla, F equals 1/2 1 Tesla, the external field, plus 0.1 Tesla plus 1/2 plus, which equals 1.1 plus, it still comes out to the same force as if there was no current. Now case 2 will increase the B1 to 1 Tesla. In other words, we increase the I1 is increased to produce B1 equals 1 Tesla. With B1 at 1 Tesla, this should be 1 Tesla. IL equals 1 plus 1 Tesla plus 1/2 1 Tesla minus 1/2. Now, because the core saturates at 1.5, the core cannot go up to 2 Tesla. So this is limited to 1.5, and this can go down to 0. So the core is only saturated on one side, on the left hand side. So the force now is IL 0.75 Tesla. F decreased because the right side saturated at 1.5 Tesla. Case 3, B equals 0.5 Tesla and B1 equals 3 Tesla. I1 is increased, I would have produced B1 equals 3 Tesla, but because the core saturation at 1.5, both sides will be saturated in the opposite direction at 1.5 Tesla, and the force will be 0. So for the formula it would be 1/2, 1.5, 1/2 minus 1.5. That's because it's in opposite direction. So saturated on both sides, it will produce them. That's why we want a large air gap for the current carrying conductor, but we want no air gaps for the external B field. Because you want to operate the B field as close as possible to saturation of the core at around 1 Tesla. It leaves little room for the B field produced by the current carrying conductor. Designed for the magnetic path for the field produced by the current in the induction coil to have a large enough air gap length such that the B field is 0.1 Tesla or less at the maximum current. At B equals 0.1 Tesla in the air, H is 80 ampere turns per millimeter. For example, the current I in the induction coil is at 10,000 amperes or 10,000 ampere turns. B for B equals 0.1 Tesla in air. H would have to be 80 ampere turns per millimeter. So the minimum air gap for 10,000 amperes is 10,000 amperes divided by 80 ampere turns per millimeter, which gives a minimum air gap should be 125 millimeters. So again, so the representation of this shielded conductor is the B field is parallel to the page. The B1 produced by the current is downwards here, and is H1. B field is upwards. B1, which is the B field produced by H1, is upwards, which is in opposite direction, so that it doesn't contribute anything to the force. And H1 is upwards here. Problem is the reverse. We want no air gap for the B field and air gap for the B1 field produced from I1. The B1 field created by the current of the conductor are in opposite direction on the sides of the current conductor, therefore cannot create a force. However, but if saturation occurs, then there'll be no force. So representing the above from another view, you can have the current flowing upwards, and there's H1 coming out of the page, B1 coming out of the page, and H1 going into the page on the right hand side, and B1 and B field coming out of the page. So what we want to do is, if we rearrange, is this equivalent to this? So what we do is we'll put the two cores here, the cores are on either side of the current carrying conductor. What about if we put the two cores on one side of the current carrying conductor? And now we will have H1 out of the page, H1 out on the page because it's on one side. But instead now we will reverse the B field on one of the cores to go inside. Will this produce a force? Because here there's a higher concentration on the left side and a lower concentration on the right side. Are they equivalent? So how we would physically implement this would be to make a core, which is a closed path like this. This is the B field coil that produces the B field, which is the black arrows. Now the current carrying conductor is placed outside the core. Now there's a large air gap here because for the magnetic path for the current carrying conductor, it's around like this through this side. So there's H1 on the same direction, but here the B field is upwards and the B field is downwards. So here the two creates a high concentration, here creates a low concentration. So what we have a closed path for the B field coil, no air gaps, and we have a large air gap for the current carrying conductor. So we want to move the core to one side of the conductor. So here's two methods of creating that: one coil and one core on one side of the conductor. So that's what we described just before. And the other method would be to have two coils and one core in the middle of the coils. So here would be a current carrying conductor going into the page, a current carrying conductor coming out of the page. This is I1, this is I2. They both produce H1 and H1 and H2 is the sum of the two produced by the both current carrying conductors, and again it will produce a high concentration field on the left side and a low concentration field on the right side. But now the force is 2 times, because this is contributing an H value, this contributes another H value, the two added together, there's two times as of H of one current carrying conductor. B1 and B2 is much less than B due to a larger gaps for B1 and B2. So another view is looking from a different view would be, we have I1 flowing parallel to the page upwards, and then you have H1 and H1 coming out of the page. Here we have a higher concentration, lower concentration, and the force is from left to right. So this is the alternate view for the one above. This is the case of one coil and one core. This is the case of two current carrying conductors and one core in between. So we're just flipping the view. So the current is flowing upwards, downwards here. The H field is into the page, but the B field here is into the page and out of the page here. Two arrangements to have no air gaps for the B field in the core, black, and the large air gaps for the magnetic fields produced by the current carrying conductor, red. The case Y, they should be equivalent by comparing with the case of two parallel wires. So we start with two parallel wires with current flowing in the opposite direction. No H field exists outside of the wire pair, since the net current is zero if viewed from outside. The H field add up inside the wires but cancel outside the wires if the wires are close to each other. So the expansive force which tends to pull the two wires apart. Now if we add a core to it, it should not change. Should still be, now add two cores as shown, the forces transfer from the wires to the core. It should have no effect on the forces as long as the magnitude of B remains the same. Change the B field direction in core 2. So we change this one from going into the page to out of the page. Now the force is changed in the direction from high field concentration to low field concentration. So the preferred method for the electromagnetic thruster, you can have two ways. You can either have the current circular and the B radial, or you can have the B circular and the I radial. So this is the preferred choice, of I circular and B radial. But we'll explain both cases. So we explain one coil, one core, and we explain two coils and one core, and the force is 2 times, the force is 0 1 time. We can also add one coil and two cores. Is the force double? I'm not so sure. Or you can have one coil and 4 cores. Is the force goes to 4 times? I'm not sure. Not sure if by adding multiple cores will increase the force. So anyway, so how physically implement that? So we have a coil here. So this is the minimum radius, this is the maximum radius of the coil, and the mean radius is the average, which is 160 millimeters. We chose 160 millimeters so that the circumference, or the length of the coil, is one loop. The length of one loop is 2 pi r, which comes to 1 meter. The formula is the same as for the motor. Thrust force, F, equals B, the magnetic field, the B field, times the current times the length. The length in this case is the circumference, the path of one loop. The external B field black, we want to be 1 Tesla. That's how we designed for. For that requires a core EG steel with no air gaps. At 1 Tesla, H is 0.3 ampere turns per millimeter. Contrast with air. For air, at B1 Tesla, we would be 800 ampere turns per millimeter. The total current the number of turns N times the current per turn circular, the coil that interacts with the external B field black, e.g. 10,000 ampere turns, one large air gap for the magnetic path for the field produced by the coil red as to not saturate the core. So here it is. Here's the air gap. Is one coil with two cores on either side, and so the magnetic path for the current carrying conductor is the red, which has to go through an air gap here, an air gap. So the total air gap is the sum of the two air gaps. While for the B field coil, there is no air gaps. So here we have a high concentration, a low concentration, which produces a force from left to right. Here we also have a high concentration on the left, a low concentration on the right, which also produces a force from left to right. Now, if you consider all different combinations, there's higher concentration here, there's low concentration, there may be a force from right to left, but also you can look at this other combination where there's a high strength here and low strength, we can have force. So those two should cancel, then we still have 2 times the force from left to right. We want to use cores to create the external B field with a high B field at 1 Tesla and therefore large lifting force. For lifting force requires large amount of current. We want the B field produced by the current carrying conductors not to saturate the core. We want a large air gap for the B field produced by the current carrying conductor. For the external B field in the core, we want no air gaps to minimize the B field coils. One current carrying conductor, this is an example, one current carrying coil and 2 cores. Air gap for the current carrying coil is red, so there's an air gap here, air gap there. And there's the other method, which is using 2 current carrying coils and 1 core in the middle. This is the preferred choice, 2 induction coils and 1 B field core in the middle. So the design of the coil. To lift 1000 kilograms, the force is mg, where m is the mass and g is the gravitational acceleration. So force equals mg equals 1000 kilograms times 9.8 meters per second squared. So equals 9,800 newtons. This is the required force to lift 1000 kilograms. Also force equals ILB, where I is the total current, L is the length of the wire, the average circumference, which is 1 meter. B is the magnetic flux density, and radial, so the flux density, which B, this is B, radial, on both sides of the coil. Choose B as 1 Tesla and L as 1 meter, and this is the start of your design. The coil average radius is R equals 160 millimeters, because we want to use 1 meter, we divide by 2 pi r, so the average radius should be 160 millimeters. From the formula, force equals ILB, force at 9,800 newtons, I with 9,800 newtons and the 1 meter length and 1 Tesla at a field of 1 Tesla, that's 9,800 amps. So let's round that off to 10,000 amperes. Choose 1 millimeter by 1 millimeter wire carrying 1 amp. I call this current I. Therefore, the total number of turns is 10,000 because we chose 1 amp per turn. Choose a square cross-sectional area. Therefore, 100 millimeter by 100 millimeters. That gives you 10,000 wires. For 1 millimeter square, the wire resistance is 20 ohms per kilometer. The total length is 10,000 kilometers. Because there's 1 meter per turn, so 10,000 would be 10,000 kilometers. 10 kilometers. The total resistance is 20 times 10 equals 200 ohms. Power dissipation is I squared R, which is 1 amp. 1 amp times 200, which is 200 watts. So 200 watts will lift 1000 kilograms. But we still need now to design the B field coil to produce a B field equals 1 Tesla. So we have the coil in the middle with the circumference of 1 meter, and we want the B field to be radial. And also we don't want any air gaps on the B field. So we want also to be able to produce 1 Tesla. So the B field is radial, the current is circular, require core to provide 1 Tesla. The coil is 10,000 amps. Coil is 10,000 turns at 1 amp per turn. Need to find a return path from top to bottom for the B field. Need to modify the cores to eliminate the air gaps. This is a different view. But how to implement a core with a radial flux density of B1 that require closed path and no gap. This core will not work. It has this core, the way it's shown now, it has air gaps. So here's the way we implement. So we modify the core to have a closed loop path this way. So the air gap for the B field produced by the coil red is 2 times 100 millimeters. So there's 100 millimeter air gap here, 100 millimeter air gap there. No air gap for the B field produced by the core black. The red coil is 100 millimeter by 100 millimeter square. Coil circular average length is 1 meter. Black coils are in the middle of the cores with circular average length of 1 meter. So core B field is 1 Tesla. Coil B field is 0, which is the induction coil, is 0.1 Tesla. The force now is double. Now it lifts 2,000 kilograms with 212 watts applied. From the BH curve for steel, 1008 to produce 1000 B field requires 300 ampere turns per meter. Choose 1 millimeter wire at 1 amp, therefore 300 turns. The total length is 300 meters for 1 coil and 600 meters for both coils, both B field coils. At 20 ohms per kilometer, total resistance is 12 ohms. Power dissipation is 12 watts. So the force is double. Now it lifts 2,000 kilograms, which is about 1.106 watts per kilogram. Now this is the preferred choice. Actually, we want the core here to extend a little bit, so the effective length is from here to about here. If each coil is the same size as the case for a single coil, 10,000 ampere turns and equals 10,000 turns, 1 millimeter by 1 millimeter wire carrying 1 amp, the square cross-sectional area is 100 millimeters by 100 millimeters. The lifting force is double to 2,000 kilograms and the power consumption is 200 watts. Two counter-circulating induction coils with 1 B field core in the middle. So this is how it looks when it's put together. 2 circular coils and 1 circular core in between. The cross-sectional view cut in the middle. This is cut in the middle. So you can see that the width and the height is 100 millimeters. The mean radius is 160 millimeters. And the H field produced by the coils are the red arrows. So the coil here is flowing out of the page, so it produces H field. Both of them produce an H field, H1 plus H2, H field going from left to right on both sides of the core. But the B field is produced by the B field coil, which is in the middle, produces a B field going from right to left on top, from left to right on the bottom. So here is a low concentration, here is a high concentration, so the force is from down to top. Here on this side, the current is going into the page. Here the current is coming out of the page. And both produce an H field. The 2H field is the red arrow going from left to right on both sides. But the B field is reverse, going from left to right on top and from right to left on the bottom. Again, there's a higher concentration here, lower concentration, so the force is from bottom to top. So I2 is 10,000 ampere turns, the same way as I1, 100 meter by 100 meter. The average length is 1 meter, and because the R mean is 160 millimeters. This was chosen, that's what we designed on purpose. Now, 1 coil and 4 cores configuration. Does it double the force? I'm not so sure if it does or not, but it does. I don't know if there's any in the acting forces which negates the additional force caused by it. I'm not sure. So we looked at the case where the current was circular, the induction coil, and the B field was radial. Now I'm going to look at the case where the B field is circular and the current is radial. And this will be the case where two counter-rotating fields with a toroidal coil. So this is a codeway. It's not very easy to understand, but the green is the core. This is the B field coil wrap around. So we'll look later. Pink is the envelope of the toroidal core. Blue line is the current path for each turn or loop on the toroidal coil. So this is how the current is. So this goes all around in a circle. So this is the current path. So there's a red circular coil around each core producing the B field. So the two B fields are in opposite direction. Here is coming out of the page, here going into the page, but the H field produced by the toroidal coil is into the page here and out of the page here. So two counter-circulating B fields inside a toroidal core. So the toroidal induction coil, blue, is around both cores. It produces DH field red going here upwards, but each core has its own coil, B field coil. One produces a B field going downwards, the other one produces a B field. So I do not show on this diagram here the B field coils. Toroidal induction coil, blue, wrapped all around both cores, produces the H field red arrows. A small coil wrapped around each core produces the B field black arrows, not shown. The problem is the toroidal induction coil is large and will saturate the cores. No force will be produced. Required that the cores contain an air gap to the H field path, but no air gap to the B field coils. So we have a problem here. It will the toroidal coil will saturate the cores. So how do we solve this? That's by folding. If you think of the whole full circle, we fold it in half. So we still do the same. The circular cores were folded in half, now still creating two counter-rotating B fields with an air gap for the toroidal coil but no air gap for the B field. So if we fold in half and we give an air gap of 100 millimeters, so now the B field was still shown here. Now I show here the B field coils for the cores. One produces a B field coming downwards, the other one produces a B field going upwards here. So there's no air gap for the B field. However, for the induction coil or the current carrying conductor, there's a large air gap because it goes all the way around. Toroidal coil produces H field arrows, 10,000 ampere turns, as large air gap. The B field coils, 4 cores, produce B field black arrows, no air gaps for the B field. So we only need a small coils, 300 ampere turns per meter. Air gap for toroidal coil is 100 millimeter. The B field coils for core produces a B field black arrows, no air gaps for the B field coils. So here's another 100 millimeter air gap for the toroidal core. Size and weight calculation for the case of a single coil and a single core. Density of copper is 8.96 grams per centimeter cube. Coil size is 10 centimeters by 10 centimeters by 100 centimeters, which is 1 meter long circular. Coil volume is 10 by 10 by 1000, which is 10,000 cubic centimeters. Coil weight is 8.96 times the volume, which is 89.6 kilograms, rounded off to 90 kilograms. Density of steel is 7.87 grams per centimeter cube. Core size is 3 centimeters by 12 centimeters because the core is very small, times 100 centimeters, is which is 1 millimeter long circular. Core volume is 3,600 cubic centimeters. The core weight is the density times the volume of the core, which comes up to 28.3 kilograms. So we run it off to 30 kilograms. So the total weight is the weight of the coil plus the core weight, which is 120 kilograms. The overall diameter is 2 times the radius, so it's 2 times 16 plus 6 centimeters, which is 44 centimeters. The overall height is the height of one coil plus the height of one core, which is 13 centimeters. Payload, it can lift 1,000 kilograms, but the weight of the device is 120 kilograms, so it leaves 860 kilograms as the payload. The AGT Thruster is scalable. There is no limit to the size. For example, doubling the diameter and doubling the height of the coil will result in increasing the volume and weight by 8 times, increasing the power consumption by 8 times from 0.2 kilowatts to 1.6 kilowatts, and increasing the lift force from 10,000 newtons to 80,000 newtons, capable of lifting 8 metric tons against gravity. So there's no limit, it's scalable. Equivalent output power calculation. Not sure if the calculation is correct since it is not defined. The EMT is floating, standing still, or not moving. Energy equals half mv squared, and v equals acceleration times time, where a is the gravitational acceleration, g times 9.8 meters per second squared. So we substitute g for a and substitute v as at, so it will be half m g squared t squared, but power is energy over time. It's a half mv g squared times t. Assuming the device was out in space for the first second and the power is 1,000. So we assume that it starts from 0, and what would be the power required or the energy required for the first second of operation. So it'll be half 1,000 kilograms times 9.8 meters per second times 9.8 meters per second squared times 1 second. It comes out to 48 kilowatts. So the amount of force can be controlled either by controlling the current to the B field coil or the current to the induction coil. Controlling the current to the B field coil by varying the current may be easier since it requires less than 10 watts. The only drawback is that it must provide constant 100 watts to the induction coil even if there is no force to be applied. This chart was taken from the website for the NASICA's superconductor thruster, where they compared to NASA's Dawn spacecraft ion thruster. So I added the AG thruster, which is also scalable, so there's no limit. But anyways, I just did it for the case of lifts 1,000 kilograms per kilowatt against gravity. So the mass to spacecraft mass, this is 35 kilograms to 1,240 kilograms. It is 1,000 kilograms to 120 kilograms. The thruster size here, it's bigger, it's 44 centimeter diameter times 13 centimeters. Power source mass, it's still 120 kilograms. The thrust, there's the big difference. 92 millinewtons for N star and 21 million newtons for the NASICA's superconductor thruster. in our case is 10,000 newtons. Lifts 1,000 kilograms against gravity. And the thrust to weight ratio here is 0.18 newtons per kilogram. Here is 62.5 newtons per kilogram. Power consumption here is 2.3 kilowatts. 0 kilowatts here is 0.2 kilowatts. Electric efficiency is 64% here. Here is over unity. Also, this one is also over unity. Power input is only, here is 0 kilowatts, here is 0.2 kilowatts. Thrust to power ratio, infinity, is 50,000 newtons per kilowatt. So this is the big difference, 50,000 newtons per kilowatt. Calculations for space travel from Earth to Mars. The distance from Earth to Mars is 54.6 million kilometers or 54,600 million meters. The spaceship will travel half the distance with 1g constant acceleration so that the crew will experience natural Earth-like gravity. At the half distance point, the spaceship will turn 180 degrees and decelerate at 1g constant deceleration towards Mars. Again, the crew will experience natural Earth-like gravity. So the crew will experience Earth-like gravity during the entire trip to Mars. The half distance point is 54,600 millimeters divided by 2, which is 27,300 million meters. The distance S is 1/2 gt squared, or t equals the square root of 2 times the distance divided by g, square root of 2 times 27,300 millimeters divided by 9.8 meters per second squared. T equals the square root of 5,571.4 million, which equals 74,642 seconds. In hours, it is 74,642 seconds divided by 60 seconds per minute divided by 60 minutes per hour, which equals 20.7 hours. This is the half point the entire trip will take. This is the half point. For the entire trip, it will take 2 times 20.7 hours, which is 41.4 hours, which is less than 2 days. The velocity at midpoint is v equals acceleration times time, which is g times time, which is 9.8 meters per second squared times 74,642 seconds, which is equals 731,492 meters per second, or 731.5 kilometers per second. The speed of light is 300,000 kilometers per second, so the velocity at midpoint is 731.5 divided by 300,000, which is 0.24% of the speed of light, so there is no relativistic effects. Conclusion. The EMT success hinges on 2 factors. The number 1, the reaction force is on a vacuum, not on another member of the structure. And 2, putting a core on one side of a current carrying conductor also creates a force on the core. Normally the H field are in opposite direction and the B field is in the same direction. It is equivalent to the H field on the same direction and the B field is in the opposite direction. This was proven by the experiment where you have a H field coming out of the page here, but the same B field coming out of the page and H field on the other side. So this was done by the experiment. A force will be transferred from the wire to the core. But we want to know if it's equivalent to having the H field the same on both cores, but this time we'll reverse the B field. Are they equivalent? Can the practical device be built? This way a practical device can be built. An experiment should be performed to prove this approach works, i.e. produces a force before building the device. So the specs and capability, again, no fossil fuels. So the logo symbol represents 2 counter-circulating currents for the case of 2 induction coils with a B field core in the middle, or 2 counter-circulating B fields inside a toroidal induction coil. So the green thruster, electromagnetic thruster, the size is 440 millimeter diameter by 130 millimeter high, or 17.6 inches diameter by 5.2 inches high. The volume is 0.73 cubic feet. The weight is 120 kilograms. The output, it lifts 1,000 kilograms against gravity and is equivalent to an output power of 48 kilowatts. Power input consumption is 0.2 kilowatts. And this is the end.